Okay, for number 41 from the book Segel, you have a reaction carried out in a tris buffer, 0.2 molar, pH 7.8. And as a result, the proton was consumed, 0.033 molar. And the questions ask you kind of similar to number 40, like the final pH after the reaction occur, but first, for part A, you have to calculate the ratio of tris base and tris acids before the reaction. So before the reaction, you have tris buffer, pH 7.8 here, right? And then because it's asked you about the ratio, so you would imagine that the solutions, the tris buffer right now would contain two components, either tris acid or tris base. And then we can calculate the ratio by using the Henderson-Hasselbalch equation. So pH equal pKa plus log B over A. So B is tris base and A is tris acid. So pH right now is 7.8 and pKa is 8.1, and then plus log B over A. So for B first, so I'm gonna change A in terms of B. So you get log B over A equal 0.3, and then B over A would be equal 10. Sorry, this is minus 0.3, and B over A equal 10 to the negative 0.3, and this equal 0.5. So I would like to solve for B, so I will change A in terms of B. So it's 1 minus B instead of A. So equal 0.5 here. So B equal 0.5 minus 0.5 B, and so you can use the shortcut. I mean, as long as you feel comfortable, it's totally okay. So B, you get 0.33 here. So A would be 1 minus 0.33 equal 0.67. So the ratio between tris base and tris acid is equal 0.33 divided by 0.67. So it's 1/2. And so that is the ratio. What about the concentration of tris base and tris acid? So you would calculate the concentration of tris base and tris acid by using the ratio times by the concentration of tris buffer. So tris base, you would have 0.33 times 0.2, and then tris acid get 0.67 times by 0.2. The tris base, you get 0.066 molar, while tris acid, you have 0.134 molar. So that value we'll use in used in the calculation of the final pH in part B. So before the reaction occurs, your tris buffer contains tris base and tris acid at this amount. So when you run the reaction and you consume the proton, what will happen? So because you consume the proton, so it means that after reaction, your tris acid here would be consumed, right? So you're taking proton out of the tris acid. So that's why tris acid, when you're taking the proton out, it will change to tris base. So if you begin with tris 0.066 molar and tris acid 0.134 molar, after the reaction, your tris acid would be decreased while your tris base would be increased. So we will have to consider about those changes because it will affect the final pH, because it will change the ratio of tris base and tris acid. So to calculate the final pH, you have to use the Henderson-Hasselbalch again. And since we already talked about the modified version of Henderson-Hasselbalch here, I would like to use the modified versions here. So start from the original version here, B over A. So as I mentioned that when the reaction occur and then the proton is being consumed, it will decrease the acid ratio of your tris species. So it means that you have to deduct the amount of proton that being consumed from the acid. And then because when you take the proton out from the acid, it will change to base. So that's why you need to add the amount of proton in the basic ratio. And now this equation is ready for plug in. So pH, you have to find, and pKa will be the pKa of tris, which is 8.1 plus log B. So the value of B is 0.066 and the value of A is 0.134. So the proton that being consumed is 0.033 molar. And before the plug-in, make sure that you have the same unit here. Is all of them are molar. Okay, so your final pH, when you calculate this, you get 8.1. So one thing to notice from this question is that when you run the reaction and then your final pH is 8.1 and which is equal to the pKa. So what does that mean? So that means that at pH 7.1 here, the ratio of tris base and tris acid will be 1:1, right? So it will contain half of tris base and half of tris acid. So instead of using this modified Henderson-Hasselbalch equation, you can also use the ice table to determine the deduction and the addition of the proton, right? So if the proton is being consumed, it means that you also generate the hydroxide ion at the same amount of the amount that you consume from the proton. So tris So you can calculate the pH from the amount of hydroxide ion that produced. You will have hydroxide ion being produced as the same amount of the proton that being consumed. So in this case, it's 0.033. So you can calculate the so you can calculate the pH if there is no buffer present in the system. So the number of the hydroxide that generated will be calculated directly into the pOH, and then you have to change pOH into pH. And so if you calculate the pH without the buffer being present in the system, you get the pH equal 12.52. So this indicates that the buffer is help you into provide the conditions that the pH remain unchanged. So you can notice that if you have the buffer present, the pH will just 8.1, but without the buffer, the pH will dramatically raise to 12.52. So, and that is how we solve for number 41 here.